Hello viewers, today in this video we are going to discuss about the bipolar transistor or also known as the bipolar junction transistor. As you can see in this diagram, the image, there are three terminals shown for each of these models. There can be different specifications of these bipolar junction transistor depending upon their doping profiles, what amount of input signals and output signals it can deliver. So accordingly you will see. Okay, so what do you mean by a bipolar transistor? Basically, it's a multifunction semiconductor device that, in conjunction with other circuit elements, is capable of current gain, voltage gain, and signal power gain. Basically, okay. So the basic transistor action is the control of current at one terminal by voltage applied across to other terminals of the device. So as you can see, there are three terminals here. Okay, so one terminal will be common to both the input and output. For example, if this is your input, this will be your output. Okay, so you can actually regulate the current, okay, by varying the voltage or current in the other two terminals. So there are three basic transistor types. Okay, so basic transistor type, the one we are discussing is BJT, bipolar junction transistor. So here you can see there are two for the types PNP and NPN. We will see in detail later. And the other type is field effect transistors, which can further be classified into two types, okay, depending upon the design of the transistor. One is JFET, which is known as junction field effect transistor, and the other one is MOSFET, which is known as the metal oxide semiconductor field effect transistor. So these are the three basic transistor types that we will see. We will do more about it later. Okay. And the bipolar transistor has three separately doped regions. Here you can see these are the three separately doped regions. You can see this one is emitter, named as emitter, the other is base, and the third one is collector. Okay. And accordingly, if this is a PNP, then you can see two PN junctions here. Okay, and if it is NPN, then also you will see that there are two PN junctions over here. So these two PN junctions are actually very close, so that the interactions can occur between the two junctions. So the base region has to be very in terms of width, if you will see, it is less. Okay, as the flow of electrons and holes are involved in this device. As you can see, we have n, p, n regions. So the flow of electrons and holes will be involved in this device, and that's the reason we call it bipolar. Okay, because of the two different polarity of charge carriers are there involved in the flow of current. So we call it bipolar junction transistor. Transistor, you can see NPN transistor, the emitter region. Here you can see double plus sign that indicates that it is heavily doped. Okay, this plus sign indicates the relative magnitude of the impurity doping concentrations. Okay, normally used in bipolar transistor. This is single plus, you can see that is moderately doped. This is heavily doped, this is moderately doped. These are the signs that indicates the doping profile of the transistor. Okay, so N double plus, N region but heavily doped, P region moderately doped, and N region least doped. Okay, so this is the doping profile we can see, and the circuit symbol for the transistor, bipolar junction transistor, you can see this is the emitter region, and as you can see, this is N region. So N region, the electrons, the flow of electrons will indicate the sign actually. So it is coming out. Okay, so that means it is an NPN transistor. Okay, and this is the base, and here this is the collector terminal. Okay, this is the circuit symbol that we use for bipolar junction transistor, and you have to be careful about the arrow that is made here. Okay, the same way we can also show the PNP transistor. So PNP transistor, emitter is always heavily doped, base region is moderately doped, and collector is region is the least doped. So here you can see it's a PNP transistor, P region, N region, and the P region. Circuit symbol, here you can see this is a P type semiconductor, so the P will receive the electrons, right? That's why the arrow is incoming. The earlier case it was outgoing. Now here in this case it is incoming. So that we need to also keep in mind. Okay, the emitter region has the largest doping concentration, as I repeatedly saying. The collector region has the smallest doping concentration. Okay, and then let us see what is the basic principle of operation of these BJT. Okay, so this one we already discussed. Doping concentration width of the base region has to be very less so that both the PN junction will interact with each other easily. Okay, now this is the basic principle of operation. You can see the diagram is simple. Okay, so emitter region, the base region, and the collector region. NPN transistor we have taken. So this is heavily doped, moderately doped, and this is least doped. Now you can see the N region is connected to negative of the negative terminal of the cell, and P region is connected to the positive terminal of the cell. So this one is actually in forward biased uh, mode. You can see N region connected to negative, P region connected to positive. Now the BC, so emitter base junction is forward biased. Now see the BC region, that is base and collector region here. So P is connected to the negative and N is connected to the positive. So this is in reverse bias condition. So BC PN junction is reverse biased and BE PN junction is forward biased. Okay, this kind of mode of operation of the BJT, we call it as forward active operating mode. So we call this kind of operation of the bipolar junction transistor as forward active operating mode. Okay, so now as the BE junction is forward biased, electrons from the emitter are injected across the BE junction, okay, into the base, right? These injected electrons create an excess concentration over here, excess concentration in the base region, okay, excess carrier concentration in the base region. The BC junction is reverse biased. This BC junction is reverse biased. We said the BC junction is reverse biased. So the minority carrier electron concentration at the edge of the BC junction is ideally zero. So there is no minority carrier concentration because this is reverse biased. This BC junction is reverse biased, right? But here you got more number of electrons getting injected from the emitter to the base region, increasing the minority carrier electron concentration in the base region, right? So this creates a large gradient. So the large gradient in the electron concentration means that the electrons injected from the emitter will diffuse across the base region into the BC space charge region now. Okay, and then it will move into the collector. Okay, so this is how the the emitter is actually heavily doped so that the electron concentration will increase in the base region, which is a magnetic carrier concentration for the base region because it is the P region. And from the P region, because of the concentration gradient, and collector is your least doped, so the electron can easily be injected through this region, even though this base collector they are like reverse biased. Okay, so the electron concentration here, the minority electron concentration V is now connected to the negative region, so it can easily be pushed through the BC space charge region. Okay, so this is the basic principle of operation, and this particular mode of operation is known as the forward active operating mode, where your emitter base junction is forward biased and base collector junction is reverse biased. Okay, then let us look at the simplified transistor relations. I will just show you the simple band diagrams before going into the current part, like what is the base current, emitter current, and collector current, and total current in the the transistor, and what is the relationship between these individual currents. Okay, before that we will see what is actually happening. So we got the basic diagram over here. This is your emitter region that emits the electrons through the base to the collector. So this is your base region and this is your collector region, right? So electrons from the emitter region through the base region, it goes to the the collector region. This is a oversimplified process of showing the injection of the electrons from the emitter through the base to the collector. So if you just look at the band diagram, energy band diagram for the transistor, it looks like this. So what we have, you can see when there is no bias, your zero bias, there was no voltage given to any of the junctions. Then we got the Fermi energy level is at thermal equilibrium, so you can see the Fermi energy level is constant throughout. Then we have this as the N region. You can see conduction and energy band and the Fermi energy level, the gap is less. That indicates this is N type semiconductor, and the Fermi energy level and valence band has a larger band gap, just to show that this is N type and heavily doped. So the distance of separation actually, gives you the idea, like, how close the EC and EF are. That shows us you know, the doping profile basically. So this one is heavily doped. As you can see, the Fermi energy level is very close to the conduction band. Similarly, this is moderately doped. The base region is moderately doped. So this gives you the separation between the Fermi energy level and the valence band for the P region. And this shows the doping profile over here. And similarly, this one is least doped, and you can see the distance between the conduction band and the Fermi energy level. In case of N-type semiconductor, this is little larger. But as there is no bias, there is no voltage given across any of the junctions, the Fermi energy level is constant. Accordingly, you can see the band bending basically. So the EC, and then you can see potential gap over here, and then the conduction band of the P region, and then the potential gap here, and then this. So accordingly, all the bands will bend, that we have already discussed in the PN junction. You can just go back and see how the energy band diagrams are made, keeping the Fermi energy level constant at zero bias, right? So this is how we got. And for the forward active mode, we said the base emitter junction will be, this one will be forward biased, and these base collector junction will be reverse biased. So as per the energy band diagram, we know that the Fermi energy level here, this in this region, will go up because it is forward biased, right? And the base collector region here, the Fermi energy level will, base collector region is reverse bias, so there will be a space charge width, larger, higher space charge width. Okay, so this will go down, and ultimately the energy band diagram, this one also is reverse bias, so Fermi energy level will be shifted right down, and accordingly band gap, this band gap will, this space charge width will increase, so you will observe more band gap here, and this space charge width will decrease because it is forward bias, so you will see less band bending here. Okay, so the ideal diagram for the forward active mode will be like this. So this one has reduced, the space charge width here has reduced, the band bending is now less, and here you can see this base collector region, this is the collector region, this is base region, this is our emitter region. So the base collector region, the space charge width has increased, and you can see the band bending. Okay, so in this particular mode of operation, you can see the electron can easily flow downhill from the base emitter region to the base collector region, and here you can see the movement is easily downhill towards the conduction band of the collector region, right? So this is just the basic explanation of the forward active mode in BJT. And in the next video, we are going to discuss about the collector, emitter, and base currents in a bipolar transistor, using the concept that we have already discussed in the, how the minority carrier concentration of electrons or holes, they flow across the junctions. Thank you for watching.